Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at lesson 5.2.2. This is called Computer Simulations of Probability. And the basic idea here is we've been working with some very simple examples of probability, and some probabilities are very, very complicated. So complicated that trying to come up with a mathematical formula to make it work right and get the proper theoretical probability is, I wouldn't say impossible. I mean, but you just really have to know a lot about how math works and how probability works. And for many, many people, that's just a little bit out of grasp. So luckily, we've got a situation where we talked about this earlier in the year, where we can conduct an experiment. And the more times you conduct the experiment, the closer the experimental probability comes to the actual theoretical probability. So if we can take advantage of that understanding and create a simulation, we can actually run the simulation, and the simulation will show us after, say, 1,000, after 1,000,000, after 100 billion simulations, which computers can do because, you know, they're so fast, they can actually give us the probabilities, because whatever results we get out of conducting the simulation 1,000,000,000 or 100 billion times should be really, really close to the theoretical probability. So let's enter in simulations. What do we have for simulations? What is the definition? Well, it's a replication or a copy of a real-life event, often using computers. Now, we don't necessarily have to use computers, but if you're going to run a 100 billion simulations of an event, you're going to need your computers because we can't do anything that fast. Okay, so simulations are just, you know, kind of like a copy or a replication of a real-life event. All right, so let's see what this has to say. If you toss a coin 10 times, what is the probability of getting a 3 or more heads in a row? If an airline overbooks a certain flight, what is the chance more passengers show up than the airplane has seats for? When 67 people get cancer in 250 homes in a small town, could that be due to chance alone, or is polluted well water or some other cancer-causing source a more likely explanation of the cluster of cancer cases? When the mathematics becomes too complicated to figure out the theoretical probability of certain events, statisticians often use computer simulations instead. Many simulations require the use of random numbers. Random numbers have no pattern. They cannot be predicted in any sort of a way. Knowing a random number in no way allows you to predict what the next random number is going to be. An example of a random number generator is a standard number queue, which randomly generates a number from 1 to 6 whenever you roll the dice. Complex simulations like modeling the weather, traffic patterns, cancer radiation therapy, or stock market swings require tens of billions of random numbers. For those simulations, a large computer running for hours or even days is needed. However, many simple simulations can be done with our Chromebooks and our simple classroom technology. Okay, so here we go. Oh, what did I do there? I forgot to erase some stuff. Let me go ahead and get that fixed. Okay. So what we have here is a random number generator. Imagine a random number generator that produces a number from 1 to 20. In each game below, if the stated outcome happens, player X wins. If it does not happen, player Y wins. So what we're going to do is we're going to explore these situations and try and figure out what is the probability of player X winning. And from that information, we could figure out the probability of player Y winning, because that would be the complement, right? And then we have to decide whether or not each game is fair, which we discussed earlier in the year. A fair game is when both players or all players involved have an equally likely chance of winning based on the probabilities, not based on their understanding of strategy, mind you, just on the probabilities themselves. Okay, so Let's start look at from this random number generator. What is the probability of getting a prime number? Okay, because if you get a prime number, then player X will win. And if you don't get a prime number, then player Y would win. So I'm going to come up here and I'm going to highlight what all the prime numbers would be. Okay, so if we remember our definition for prime numbers are all the numbers that have exactly two factors, the number 1 and itself. So technically, the number 1 is not a prime number because it only has one factor, just the number 1. But 2 is a prime because that's 2 times 1. 3 is a prime because that's 3 times 1. But 4 is composite. It's 4 times 1 and 2 times 2. So that is not a prime number. So 5 is a prime, 6 is not. 7 is a prime, 8, 9, and 10 are not. 11 is a prime number because it's just 1 times 11, but 12 is not because you got 2 times 6, 3 times 4, and 1 times 12. So that's composite. 13 is prime. No, no, no. 17 is prime, and 19 is prime. So how many total prime numbers are there in this set of numbers between 1 and 20? You got 1, 2, 3, 4, 5, 6, 7, 8. All right. So that means we've got probability of 8 out of 20 for a prime number, which means X has a 40% chance of winning. Okay? Does that make this a fair game? It doesn't really, because that means that Y has a 60% chance of winning this particular game. Okay? Now let's take a look at the second situation. Oh, I should probably get rid of all of those highlights there because they're not going to apply to game number 2. Okay, an even number. So let's highlight all the even numbers. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Count all those up and you'll see that 10 out of the 20, or half of the numbers, 50%, are even numbers, which means that the other half have to be odd, which makes game 2 actually a fair game, right? Because they both have an equally likely chance of winning. If the number's even, X wins. So if it's odd, Y wins. They both have the same chance. And then for the last situation, a number not divisible by 3. So what I'm going to do is I'm going to cross out the ones that are divisible by 3. Okay, so 3, 6, 9, 12, 15, 18. That leaves 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of the 20 numbers are divisible by 3. And that's 70% of the numbers, which means X has a chance of winning game 3 70%, which means that Y only has a 30% chance. So now that we've got all of the theoretical probabilities that X wins and that Y wins, which game is the fair game? You see it right here, right? It's only game 2 is the only one that would be considered a fair game in this set of games. So in which of these 3 games is X more likely to win? Well, which one does X have more than a 50% chance? That would be game 3, right? Because player X has a 70% chance of winning this game and player Y only a 30% chance. So in game, let me go ahead and get rid of these guys there. In game 1, the prime number game, if you play 40 times, how many times would you expect player X to win? What if you play 50 times? Okay, so why don't you go ahead and take a little time and see if you can figure this out. We're dealing with this probability right here, okay? If you play 40 times, right? If you play 40 times, how many times would you expect player X to win if the probability is an 8 in 20 probability? All right, go ahead and pause and see if you can work that out, and then unpause when you think you've got an answer for both if they play 40 times and 50 times. All right, hopefully you've had enough time to sort through this. All right, so I want to give you a little bit of background information. I just want you to understand, make sure that you understand. If there's an 8 in 20 probability of winning game number 1 for player X, let me go ahead and scroll this up a little bit. Then that means if player X played this game 20 times, we expect them to win 8 of those 20 times. That's what this probability literally means. It doesn't mean that they will only win 8 times. They could win 10 times. They could win 15. You never know because it's a random number generator that's coming up, okay? Um, we expect it to be 8 out of 20. That's the theoretical probability. So if that's the expectation, then if you played twice as many games, you would expect to win twice the number of times, which means that we would expect player X to win game 1 16 times if you played the game 40 times, okay? So how many times would we expect them to win if they played 50 times? Well, you're just using proportional reasoning here. So whether you choose to look for a giant 1, cross multiply, whatever technique you choose to use, some students might even simplify this fraction down to 4 over 10 to make the giant 1 easier to find. You end up getting 20 as your answer. So we've got, if you played 40 times, you would win 16 times. And if you played 50, you should win, I should say, 20 times. All right, there's no guarantees there. Now, I do want to bring up something with the online book here. Each one of these particular situations has a student tool that you can use. So you click on that student tool, and it says click the box below and play all 3 games. All right, so we could actually keep a tally here. And I think I'm going to do that right now. I'm going to do game 1, which was if you get a prime number, player X wins. And I'm going to hit this 20 times, and I want to see how close we get to 8, right? Let's just go ahead and do it. 7. Wait, are you going to go or what? Oh, no. There we go. No. So that's 1 is a no. No, that's 0 for 2. 1 for 3. 2 for 4. 2 for 5. 2 for 6. 3 for 7. 4 for 8. 5 for 9. 5 for 10. So far, 50% of the time we've gotten prime numbers, 5 out of the 10. That's higher than our theoretical probability. Let's see if we do it another 10 times, if it'll drop back down to 40% of the time, or 8 out of 20. So we're at 5 for 10, 5 for 11, 5 for 12, 5 for 13, 5 for 14, 6 for 15, 7 for 16, 7 for 17, 7 for 18, 7 for 19, 7 for 20. All right, so we actually got 7 out of 20 instead of 8 out of 20 when after the first 10 it was 50%, then it dropped down to 35%. If we did it another 20 times, I'm guessing it would get closer to 40%. So it started at 50%, then it went down to 35%. It'll probably creep up a little bit more and get closer to 40. And then if we did it 100 billion times, I bet you anything it would round off to 40%. So there's one of our number generators. And by the way, you can use these for your, if you want to create your own heads or tails, your own dice, your own bag, or here are some cards. Here's this guy right there. You can choose how many numbers you want to have there. And you can choose if you want to go from numbers 1 to 2 or 1 to 3 or 1 to 4. And once you get that set up, then we can do little simulations with this as our tool. But we're not going to do that right now because we're going to move on to the next problem. So let's see what the next problem says. All right, Janelle is going to babysit her nephew all day 5 times this summer. She had the idea that one way to entertain him was to take him to McBurgers for a kid's meal for lunch each time she babysits him. The kid's meal comes randomly packed with one of 3 possible action figures. Janelle would like to know the probability that they will get all 3 figures in the 5 trips. Okay, so you could literally see this guy right there. You could literally go all 5 times and get this person every single time. Okay, or you could go one day and get him, the next day get another one, the third day get him, the fourth day. So you never know which one you're going to get. It's always randomly packed. So what we're going to do is we're going to set up a simulation like I had just shown you with those numbers. And we're going to call action figure number 1, maybe this guy. Number 2 will be a different action figure, and number 3 will be a third one, which we don't have pictured here. Okay, and so we're going to try and what do they say? They say to use the random generator to simulate 5 trips to burgers. Okay, so here we go. Let's jump onto the online tool for this problem, which is problem number 35. Click on that. All right, so this is not what I want here. I need to set up my probability tool where I take this guy and we want a total of 5 trips, right? And we got action figure 1, figure 2, and figure 3. So let's get rid of this guy. That's useless there. All right, so here we go. We're just going to take one trip or 1 week scenario. So this would be day 1, this is day 2, this is day 3, this is day 4, this is day 5. So when I click on it, we're going to see if we get all 3 action figures in those 5 days. Ready? Let's go. And the answer is no, we did not. We failed in our mission. We got only 2 different action figures. We got 3 of these guys and 2 of those guys. So it did not work in that particular week. So there's no guarantee, right? We could have gotten all 1s, all 2s, all 3s, or in this case, we got only 1s and 3s with no 2s. So did we get all of them? No, we did not. That's the answer. So now let's make use of our simulation and see if we can figure out what the probability is going to be for this to work for Janelle. We're going to do this at least 20 times, okay? So let's start over. And how am I going to do my tick marks? I better use a separate piece of paper and keep track of this because I am notorious for losing track of what count I'm on, which means I'm going to have to get up and I'm going to have to go find a piece of paper and a pencil. Hold on. All right, I could not find a pencil and a piece of paper handy, but luckily I'm going to make the technology work for us here. Can I find my pen in there? Where's my pen? Hold on for a second. Make sure I got my pen working. Now I'm gonna, no, I don't want to do that. What do I want to do here? I want to do that. Yes, I'm sorry. So, okay, so here we go. I'm gonna click on this and I'm gonna either say yes or no. Maybe I better keep a tally here of all my yeses. And a yes means yeah, we got all 3 of them, and a no means we didn't. And we're gonna keep going until we have a total of 20 in here. Okay, so here we go. No. Yes. 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 No. All right. At this point, after only 5 simulations, it appears as if 3 out of the 5 were yeses, which is 60%. Let's see if that holds up. Yes. Yes. No. Yes. No. That is 6 out of 10 are yeses, which is also 60%. That's pretty interesting. Let's do it a total of 20 times now. This is out of 5 and out of 10, it was 60% chance of success. Let's see if that holds for 20. No. 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 Uh-oh, this isn't looking good. Yes. No. No. Yes. Yes. I can't remember if that other one go. We're going to say it didn't work. Okay, so now we've got 9 out of 20, which is the same as 45%. So it started off strong, but then kind of didn't work in our favor. You know what? I really, really want to try. Let me go ahead and I don't want to clear all the ink. What do I want to do here? I want to do this. Let me do this. Get rid of that. Another 20 times and see, because the more we do it, the closer it should come to our theoretical, right? So let's keep going. Do I have my pencil here? No. Oh, come on, pencil. Where are you? There you are. Okay. No. no, no, yes, 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 no, yes, no, yes, no, no, yes. What do we have? 5, 10, 15, 20, 25, 30, 31, 32, 33. All right, I got to go 7 more times. No, 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 yes, yes, no, no. Okay. 5, 10, 15, that's 17. 5, 10, 15, 20, 23, that is a total of 40. And it was 15, it was 17 out of 40, which is what percent? 17 divided by 40 is 42.5%. All right. So according to this simulation, let me go ahead and expand this guy out. Let me come back to here. According to this simulation, should she be worried? Yes, because it only worked 42.5% of the time. So how could Janelle get an even more accurate estimation of the probability? Well, if she did the simulation 100 times or 1,000 times, that would work, right? So if you do more simulations, that will give you a more accurate probability. All right, so what fun. There's our record. All right, now let's try something different. Janelle's aunt and uncle have 3 children, 2 of whom are girls. Assuming that girl children and boy children are equally likely, Janelle thought that the chance of having 2 or more girls out of 3 children must be 50%. Janelle's brother thought the chance of having so many girls had to be less than 50%. What do you think? Okay, so it says make a conjecture about the probability of having 2 or 3 girls in a family of 3 siblings. Okay, so I'm going to highlight. It is actually, let me use this color. Probability of having 2 or 3 girls. What do you think? Now, obviously, because this is video and you're doing it at home, you're not going to be able to share your thoughts with me. So just think about it on your own. Do you agree that with Janelle that 50% seems logical? But we're talking about 3 kids, not 2 kids. Does that change it at all? Something to think about. Okay, so now we're going to do a simulation with the random number generator. I actually don't want to do the random number generator for this. I'm going to make a simple list, and we can actually figure out our theoretical probability based on this list. Okay, it's an organized list, but it will work. Okay, so it says use one. No, we're not going to do that. And it says do enough trials to get a good estimate. I don't want us to spend the time doing the simulations. So let's just go ahead and let's create a list where you got child number 1, firstborn, secondborn, thirdborn. And what we're going to do is we're going to start making a list of all the possible combinations. And let's start with all girls. So we're going to key on the oldest child. The oldest child is going to be a girl for a while. So if you've got all 3 girls, right? Girl, girl, girl. Then what if the third child wasn't a girl but was a boy? I'm sorry, the second child was not a girl but was a boy. That would be girl, boy, girl. And what if the second child was a girl but the third one was a boy? And what if the second and third children were both boys? So this covers every possible combination where your oldest child is a girl, but you have 3 kids, right? It's either girl, 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 boy, girl, 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 boy, or girl, boy, boy. And now we do the exact same thing, but this time we make the first child, the oldest, be a boy instead. So boy, boy, boy is a possibility, or boy, girl, boy, or boy, boy, girl, And then, of course, you could have the oldest is a boy, but then the other two are girls. So this exhausts every possible combination that we have for the siblings. So let's go ahead and highlight if the ones that are all boys, there's only one of them that's all boys, right? Only one. And then all girls, there's only one of them that are all girls. And two boys and one girl. Two boys and one girl is right here. Two boys and one girl is right there. Two boys and one girl is right there. So there are three of them. And then two girls and one boy. Here's two girls and one boy. Here's two girls and one boy. And here's two girls and one boy. So what we get is the probability of having all boys, 1, 2, 3, 4, 5, 6, 7, 8, is a 1/8 probability. The probability of getting all girls is a 1/8 probability. The probability of getting two boys and a girl is a 3/8 probability, and that is the same probability for two girls and one boy. Now, what was the question asking? It was assuming, okay, where is it? The probability of having 2 or 3 girls in a family. Okay, so that would mean that this is 2 or 3 girls, right? There's a total of 4 out of the 8, which is a total of 50%. Okay, so that is the theoretical probability, and Janelle was correct. Of having 2 or more girls would be 50% chance of that situation. Of getting exactly 2 girls, that's a 3/8, which would be like 37.5%. Okay, or getting all girls, that'd be 1/8, which would be like 12.5%. But if it's 2 or 3 girls, then that's 3 plus 1 is 4. 4 out of the 8 is equivalent to 50%. And that's where we end today's lesson. So let's go ahead and move on. I'm not sure if there's a check for understanding today, but there's definitely going to be homework. So let's move on to the next activity. Take care. Bye.
Hey, feeling good.